So hello guys, I hope you're well. So we are back the crank rocker mechanism that we have created. So remember I did not show you how to create an output talk for this part here. So what we are going to do, what we'll work on is that we are going to create an output talk request for this motion 1 or the motion 0. So you come here to the outputs. So you want to delete this first so that I can redo it again. So I had done it. So the first thing that remember when you were doing this, we did not check this, so everything was 0 0 0 0 like that. And now if you have in such a situation, let me show you something. In such a situation, if we create the output request, we'll get something different. So let's create a talk output request. So for motion 0, because the motion is here, so we say talk output. Talk output for the motion because you are going to create other talk outputs. So here we say expressions, and then here we come here, we do that, and then we click FX. So make sure your cursor is in between the front dashes. So we come to the is it motion or force. We want to create a talk output request. So it was which one? It's not by stop for the motion. Yes, so motion. So like that, so you go to force and then motion, and then here you come here to motion, which motion you want to put for. So it's motion 0 because that's the one that we have. So and then we say add. So remember there are no IDs here, so we say evaluated, but we cannot do that until we add the numbers here. So 0, so we add 0 7 0. So as I said, this for the J flags for the output markers, which we'll do today. And then 7 is the return for the talk, and then 0 is for the global reference frame. So once we say that, we say OK like that. And now once we do that, we come to the run button, and then we say run. Once we close like this, and then we say plot, you realize that once you come to the expression, actually I misspelled this, but it's okay. So we say apply, you'll get only a flat line. Why are we getting this? Is because we have not put any center of mass here. So let's come now and calculate the center of mass. Get properties from associated. Center of mass is the inertia and the mass itself. So we have to put this so that it works like that, like that. And now once we do that, we come again here, we run. The output request has not changed. So once we do that, we come and run, and then we plot. So as you can see, it's now the talk output request is like this. So you can just come here again and we can plot. So F2, we apply. You see now it's okay now. Now it's okay. Now we can even come and see the animation itself if we want to animate, but I believe we've done that. So this is for the talk output motion. Yeah, just like that, as simple as that. So now let's start today's tutorial. So today now we want to add driving torque here, and for us to add the driving torque, we need a point. We need that force to be acting on this crank and also on the point here. Now, so for us to do that, we come here, we add a driving torque. So you right click this arrow. So you say driving torque like that. Then you say okay. And now we want it to be action reaction because we want it to act on a body and at a point. So we want the body to be crank, and also we apply force at point 0. So we want it to be like that, and then here we change to rotational like that. Then rotational properties, we need to put a value here. Let's put 180. And then once we do that, now we can come, we need to save this file, save as. So we can save as driving torque like that. So we replace that one. So the other thing that we need to come and check is if we have these ones are active, they are not active. Now once we do that, we come here and check our motions. We deactivate this motion because we don't need it yet. So once we deactivate this motion, remember it's a kinematic. Now once we deactivate it, you'll find that now this will be a dynamic analysis because it has 1 degree total estimated DOF not count, it's 1 degree of freedom. Now it will be conducted as a dynamic analysis. So now let us come and run this simulation and see what happens. So we come to the simulation settings. So here you can change, you put 0.005 or you can reset to default, whichever way you prefer. Now we have to make sure that this crank is rotating. That's our main, because we are inputting a torque here, so it has to rotate. So once we click run, so let's check what happens. Solver failed. As you can see, there is something that there is this warning here. So you can come here and view the log. So we expand this and then we see what happens. So we want to check analysis if there is any error. So it's a dynamic simulation because it's not fully constrained. So warning. So there are several warnings. So that's because of we have not put the mask properties. So let's come to the animation. Nothing. As you can see, nothing is happening because these are weightless. In short, the software is taking this as weightless bodies like air. Even air is not weightless. So to fix this, you just come here, get properties, come here, get properties, come here, get properties like that, and then we save our model like that, and then we rerun it again. Now I believe there are no errors. No errors. There are no errors. You see, it's a dynamic analysis. So there are no errors. Now we come to animate. So we refresh. Now you see how it's going. That's what we want. But now the crank is fully rotating. What if we want to limit how it's going? So for you to limit, we add a limiting torque. So you can add a limiting torque. Come here. We want to add a limiting torque on the rocker. This one. So you come here, we click, right click, add a limiting torque. Limiting torque like that. And then once we add a limiting torque, now we need now to come and add action reaction, and then we say it's rotational, and then we come here to the body. So which body is the rocker and which point? Remember our points. If you forget your points, I think it's point 2. If you forget them, you can easily come here to the points and retrace which point it is. Now we've added there. So rotational properties. Now for rotational properties, we are not going to use, it's in the Y. Why do we put in the Y, not in the Z? Because the rocker itself is rotating about the Y-axis, or the joints themselves are rotating along the Y-axis, and then the displacements and the velocities are along the Z-axis going up and down, not the X-axis. So we come Ty and then we say expression like that. Once you come to the expression, you click this. Once we click, not we click there, sorry, we want to add a torque which would regulate this motion. So you have to put some angles and so on and so forth. So now we are looking for buy stop. That's what we want. We want to look for a buy stop here. So we come here, can delete that. So we want to add something here. So but for us, we can just easily do this. Let's do this. We say f of x. Now here we want to add a limiting torque on this rocker. We want to add it here so that it prevents this the crank from doing one complete revolution. So you come to the general, so you make sure your cursor is there, and then you click by stop like that, and then you come to the motion because you want to do displacements along the Z axis. Now we come here to the AZ, and then once you are there, we come to joint 0 because this is the joint that you want to constrain. So we're adding the torque here to constrain a joint here. So you're adding a torque here which constrains the motion of this crank. So let's come to the joints because we know it's joint 0, and then now you come to marker I because that's what we want. So remember, we have to put our cursor inside the curly brackets, and then we put ID string like that. Then once we do that, we say we add that. So and then because now we've done for marker I, we do the same thing for marker J. But now for marker J, you have to put a comma there, and then you put curly brackets like that, and then you make sure your cursor is inside there. And now we come down here, add string, and then we say we add like that. And now once we do that, now this is the displacement. Now we want to do the same thing for the velocity. Now you come in between those two commas there. We have to fill everything in between these commas. Now you come here now, the motion. With the first derivative of displacement is rotational displacement. It's angular displacement. So it's WZ. So you click WZ, and now we do the same thing. You come to properties, and then now you come to joints, joint 0, and then you come here, marker displacement. So marker I, and then we make sure that our cursor is inside here like that, and then we say we add, and then we do the same thing now for marker J. So comma like that, and then now we do the same thing for marker J. So we come for marker J, and then we put its string, and then we say we add. And now the next thing that we want to do is to put our deflection angles, the displacement, the upper bound and the lower bound. So I want it to go by 15 degrees. So we say minus 15, this is the lower bound, times pi, so that we can convert it into radians over 180 degrees. We are converting into radians because you cannot multiply degrees and length directly. You have to convert it. Now the other one is 15 times pi, that's the upper bound, over 180, like that. Now once we do that, now the next thing that we want to define is the stiffness value, which is 1e power 4, 1e4, like that. And then now the other value is the deformation characteristics. All these values are already predetermined according to this exercise. And now the next one is the maximum damping coefficient. So you can say it's 100. And then the last one is the penetration value for the damping, at which full damping is complete, is done. At this is in millimeters. Now we click evaluated to see if everything is okay. So now everything is okay. As you can see, everything is okay. So now we say okay, like that. Now we can come here. Now we run our simulation again, then we see what happens. We've added a limiting torque, so you can come here and animate, refresh. You see now it has limited, it's not rotating all the way. So that's how it's behaving. Now what we need to do now is to plot. We want to create an output request. Remember, these are dynamic analysis. We'll create an output request for both the dynamic and the kinematic analysis, and we can observe the difference. So we come here now. We want to create an output request. So we right click. We can right click. Do you have any outputs here? So we can right click here, and then you can add output, and then you can call it limiting torque, like that, output, like that, and then we say okay. And now once we come here, we say expressions, and then we come to F2. Here we click that, and then now here we come to motion. Is it motion or force? So V-torque, we want that one. So we make sure that it's in between. Remove the 0, and we do this, add that. And now we need now to add to put our V torque here. So we come to properties and then we come to forces. Limiting torque is there, and then it's string like that. We add that, and then now these ones we remove just as we have always done. We do this 0, 7, 0 like that. Evaluated. Yeah, it's okay. Now we say okay. Now we run this again. So we close. Remember, these are dynamic analysis, and then we come again. We say we plot. So once we come to plot, we come expressions, limiting torque output like that. Lie. So this is what we expect. So let's animate it. So as you can see, the displacements or the torque is diminishing as it goes. As you can see, it's like that. It's reducing as it goes. So now we want again to come. The next thing we can come and do here, we can return back the motion, we can activate, we can reactivate it. We reactivate it. Now if we check the model, you'll find now the DOF is 0. Now it's fully kinematic. Now you can do that, and now we can run. We run it, and then we want to plot, and then we see what happens, if there's a difference or not. So let's see if the kinematic analysis, I believe it is. You can always check here. Kinematic analysis is not dynamic, as you can see. Now you can come here and plot. Now you can see it has changed. The graph has changed now. As you can see, the torque is this now starting somewhere, and then it's reducing like that. Like that. So you can come here and then you can animate. We refresh. Yes, like that. So now this is how it's going now. Now this is the torque that we want. We come here, come expression. Let's do this. This one, F2, we apply. So that's how it's going. Yeah, so that's the difference between the two. Now the next thing that we want to do is there's this error. Nonlinear system solver could not converge. I want us to solve this error. So now in this tutorial, there is an error that we want to take care of about convergence integrator. So this error is usually incurred when you do some simulations. And now in this mechanism, we've added a torque here. So this torque, as you can see, we've added it on this joint and on this body here. So we've added, you have this mechanism. So this is a good example. In the other example for the crank rocker, you observe that it was not simulating. So you want to do something. So let us run this analysis. So I've already added a torque. So we run again. Let's run it again. Yeah, as you can see, we have an error encountered in analysis, as you can see. So let's see this error. So you come and view the log. So we expand on this, and then once we expand on this, we can come here. So it's dynamic because it's not fully constrained. That's what the reason why is because we disabled the motion that was here. That's why it's dynamic analysis. It has 1 degree of freedom. So the nonlinear system solver in the time it could not convert. This is the error that we are taking care of. The nonlinear system solver in the time integration could not converge. So we want to take care of this. So in such a case, let's animate and then we see what happens. As you can see, nothing is happening. It's just jumping from step to step and so on and so forth. So to take care of this, we come to the body. As you can see, we have not put inertia and mass properties. So we check that the free body part is okay, and then we also check this. And then once we do that, we save this model. And once we save it, we can run, and then we see what happens. So now we don't expect it to have any errors. Now you can see now it's integrating per time step. So you can increase this time step at the simulation settings. You can increase this. so that it goes very fast. So we close, then we come and animate. So let us see what happens. Now you see how it's behaving. Now let's see if we can do something about this. So you can come here now to the free body 0. So you can see this free body part. So we can uncheck that and then we leave it like this. And also this one can uncheck and then we do this. So we put like that, and also body 1. So you can change the simulations in the simulation settings, so you can change the time step from this part. So let us run this. So it has finished very fast. As you can see, it's very fast. So let us see if it has changed anything, if we can take care of this. Yes, now you see, yeah, now we've taken care of that problem that was there. So that marks the end of this video. Yeah, so yeah, that's it.